The thing we're going to do today is we are going to work on figuring out how much the mass of the gas in this classroom is. So if we were able to bundle up all the air in this room, I want you to be able to figure out how much all the air in this room would weigh, which basically means we got to get ourselves to a way that we can count particles in gases. So let's first of all take stock of everything that we know so far. Things that we know so far. We know from our gas simulation that to describe a gas, it takes 4 different characteristics. To know everything there is to know about a gas, you need to know what's its pressure, what's the volume of the gas, what's the temperature of the gas, and inside the container, how many gas particles are there? And those are the things that came out of our introduction to gases activity and working with the little simulation where the particles were bouncing around. And out of that simulation, the most important central idea was that the pressure of a gas is caused by the particles colliding with the walls of the container. So conceptually, if you need to think about how any of these things are going to influence the pressure inside your container, you just have to think about how those things would influence the number of collisions with the walls of the container. And since collisions is what causes the pressure, you'll know how it's going to impact the pressure. If we extend that and then start to think about trying to get this to no pressure at all, there's 2 ways that you can end up with a container that has no pressure inside. Possibility number 1, there's nothing to hit the walls. So you have no particles in the container. If there's no particles in the container, none of them are going to hit the wall, you're not going to have any pressure at all. We call that a vacuum. Possibility number 2, the particles never get to the wall. Okay, so they're there, but they don't make it to the wall, which, if we go back to our gas simulation, we can consider how that would happen. Put some particles in our container here, and they start hitting the walls, and those collisions cause the pressure inside of our container. We've learned that temperature tells you something about the speed of the particles. So if I cool the temperature down, the particles get slower and slower and slower and slower. And at some point, those particles are going to stop moving, and the simulation won't let me go that far, but there is a point that the particles are going to stop moving. And once they stop, they'll never get to the wall, and therefore they'll never collide with the wall, and therefore we will arrive at 0 pressure. So that's the other possibility. The particles aren't moving. They're there, but because they can't move, they're never going to get to the wall to bump into it. Particles have stopped moving is the definition of something called absolute 0. It is absolutely as cold as we can get. It's the end of the line. Once you accept that temperature is a measure of how fast the particles are moving, you realize that there's a limit to how cold something can get. Once the particles have stopped, you can't get any colder than that because you can't be less fast than not moving at all. And so that is the end of the temperature scale. The particles have gotten so cold that they simply aren't moving anymore. That's what's represented by this graph down here. This is the graph of pressure versus Kelvin temperature, and you'll notice that at the origin, 0, 0, the pressure is equal to 0 atmospheres because the particles aren't moving. They never get to the wall, they never have a collision, and at that point, the temperature is 0 Kelvin. 0 Kelvin is equivalent to absolute 0. This other graph is a picture of pressure versus the Celsius temperature scale. It is this graph extended backwards. We talked about kind of keeping on going down until the pressure is equal to 0. Well, this is the graph if I sort of pull things sideways so that we can see where we actually do hit pressure equals 0. On the Celsius temperature scale, pressure equals 0 will happen at negative 273.2 degrees Celsius. So water freezes and turns to ice at 0 degrees Celsius. And if we go 273.2 degrees colder than that, all particles are going to stop moving and stop rattling around. Well, that tells you that 0 Kelvin is equivalent to negative 273.2 degrees Celsius and gets us a conversion factor between the temperature in Kelvin and the temperature in Celsius. So our temperature in Kelvin is equal to the temperature in Celsius plus 273.2. And that conversion is right there on your resource sheet. So under temperature conversions, there's your Kelvin to Celsius. This 273.2 actually does have more digits. We're just only going to have it out to the tenths place. This is an addition operation, so you're going to have to pay attention to place when you make your decision about how to round things. All right. On the flip side here is the other graph from our Science Practice 7 exercise, the graph that plots pressure times volume versus amount of gas times temperature. And we learned a few things about this graph. We identified the slope of this graph as being 0.08206 liters times atmospheres per mole times Kelvin. That number is actually going to be extremely important to us as we start to quantify gas behavior. That number is so important that chemists have given it its own symbol. For reasons that I really don't know, it's been given the symbol capital R, and capital R is called the ideal gas constant. This number is a constant regardless of which gas you're talking about. So no matter what gas you use to collect this data, the slope of this line is always the same. And then we wrote an equation for this line, which was the stuff on the y-axis, pressure times volume, is equal to the slope, 0.08206 liters times atmospheres per mole times Kelvin times the amount of gas times the temperature. And we said that this number was given the symbol R, so the pressure times the volume is equal to R times the amount of gas times the temperature. And then, again, for reasons that I really don't know, instead of leaving it like this, when chemists write this equation, they write it as PV equals nRT. But it doesn't matter because we know if those are all multiplied together, we can put them in any order we want to put them in. And this thing, PV equals nRT, is called the ideal gas law. This is going to be the equation we use to calculate any information we want about gases. The ideal gas law is also on your resource sheet under counting particles. PV equals nRT, and here's your value for the ideal gas constant. So that's the last thing we have under counting particles, is to count particles in gases. The limitation here has to do with the units on R. The units on R are liters times atmospheres per mole times Kelvin. That's going to limit the units on all the rest of these numbers that you might want to plug into the ideal gas law. So before you can use the ideal gas law, you have to take your pressure and convert that to atmospheres. You have to take your volume and convert that to liters. Your amount of gas has to be expressed as number of moles. And the only reason I didn't write just moles there, that I wrote number of moles, is that it makes the symbol N make a lot more sense if you think about it as number of moles. And your temperature is going to have to be expressed in Kelvin. So the units on the ideal gas constant limit the units that can be on the rest of those numbers. Let's try one example here. We can use this to calculate the pressure inside the little butane cans that run our Bunsen burners when they're brand new. The can contains 155 grams of butane in a can with a volume of 242 milliliters. And the temperature in our room, in this case, we're going to call it 20.6 degrees Celsius. We'd like to find the pressure. For gas law problems, the easiest way to set up your information step is to set it up to look just like the ideal gas law. P equals, V equals, N equals, R equals, and T equals. And we need all that stuff because the only equation we have to deal with gases is PV equals nRT. And so we got to find all the parts and pieces that are going to go into that equation. R is easy. It's always the same. 0.08206 liter atmospheres per mole Kelvin. Now we're just going to read the little story, and we're going to figure out where all the rest of these numbers go. What's the pressure? That's what I don't know. Inside of a can of butane, the can contains 155 grams of butane. That is probably more related to number of moles of gas than it is to anything else in this list. So I'm going to stick that one right there. With a volume of 342 milliliters and a temperature of 20.6 degrees Celsius. Before I can use the ideal gas law, I have to make all the units match the units here. So I can't use my volume as milliliters. Instead, I have to convert that to liters, but I have a conversion factor on here that a liter is equal to 1,000 milliliters. So 1 liter, 1,000 milliliters, 0.342 liters. N is number of moles, so I can't go with 155 grams. I've got to convert that into moles. Butane is C4H10, so I can calculate the molar mass here. .124 grams. So we can get that into moles. 155 divided by 58.124. .67 moles. The ideal gas constant is fine. It's the whole reason we're monkeying with the rest of this stuff. And temperature has to go into Kelvin. I've got to add 273.2. All right, now we have everything in the units that match the ideal gas constant. Then I'm going to take my equation and I'm going to rearrange it for what I want to find. I need to find the pressure, so if I divide both sides of the ideal gas law by volume, the volumes cancel, and I end up with pressure is equal to the number of moles times the ideal gas constant times the temperature divided by the volume. Plug it all in. Pressure is going to be equal to the number of moles, 2.67, times the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. And yes, I want you to write those units every single time. The reason being it will remind you to get the rest of your units correct. Times the temperature, 293.8 Kelvin, divided by the volume, 0.342 liters. And if I look at what's going to happen to the units here, moles cancels with moles, Kelvin cancels with Kelvin, liters cancels with liters, and I'm going to be left with units of atmospheres on the pressure. And because this is all multiply divide, I can dump it all into my calculator and I can round to the proper number of significant figures when I get done. 2.67 times 0.08206 times 293.8 divide by 0.342. 3 significant figures, 4 significant figures, 4 significant figures, and 3 significant figures. Keep 3. (188 atmospheres). All right, there we go. The ideal gas law. So that can then help us with determining the mass of the gas in this classroom. So come on up and grab one of these. So to keep this from becoming overly complicated, we are going to pretend that we did this before they put the furniture in the room. Okay? Because we don't want to have to go around and calculate like what volume of space is occupied by all of the tables, what volume of space is occupied by all of the chairs, or even worse, what about us? Like, watch this. A Dorner-sized piece of gas just had to go out the door to allow me to come into the room. Every single one of you who walked into my room today shoved a piece of gas the size of you out the door. That's going to be your disturbing thought for the day. Every time you enter a room today, you need to think about the you-sized piece of gas that had to go out the door to let you come in the door. So we're also going to pretend none of us are here so we don't have to worry about all the gas that went out the door when all of us came into here. So the first one is a jelly bean contest. You're literally making a guess with not much basis to go on. How many pounds of air do you think might be in our classroom? Make a guess. You and your table mate do not have to agree on the guess. How much do you think all the air in this room weighs? All right, so just write down a guess. You are literally taking a shot in the dark here. All right, number 2, what is here with us? We have learned along the way that our atmosphere is mostly nitrogen, followed by some oxygen. Here's a pie chart that actually kind of shows you what's in our atmosphere. Nitrogen is 78% of our atmosphere. Oxygen is 21% of our atmosphere. Carbon dioxide gets a lot of publicity, but it's only 0.04% of our atmosphere. Argon is actually the third most abundant gas in our atmosphere. And then there's everything else. If we want to know the molar mass of air, we have to do that weighted average thing that we did when we calculated the mass of all of the elements. So if we want to know an average molar mass for the air in our room, we can do 21% times the mass of oxygen plus 78% times the molar mass of nitrogen plus 0.04% times the molar mass of carbon dioxide. And if we did this for all the gases in Earth's atmosphere based on the amount of each of these gases present, you come up with 28.97 grams is equivalent to a mole of air. So this is what we're going to use for the molar mass of atmospheric gases. Okay, then we need the conditions in our classroom today. So we've got some devices that are going to help us out here. This is a temperature probe, okay, and the temperature probe says 22.3 degrees Celsius. And I have a pressure probe here that says 98, we'll take it at 98.1 kilopascals. Now, we really don't measure pressure anymore using barometers. We do it in a much more electronic sort of way. So here are the devices that were used to take our measurements. Our temperature probe looks like a thermometer. This is a gas pressure sensor. It's open here on the end, so there's a little hole that comes out to the outside world. And just inside this hole is a little membrane. And as our atmosphere pushes on that membrane gets pushed in or less pushed into the device depending upon the pressure out here. It's a little bit like your eardrum. It's a flexible membrane that changes based upon the pressure on the outside. And then this is just hooked to my computer where there's software to turn that information into a pressure. So that's more how we do pressures nowadays instead of mercury barometers. And then the volume of our room. This was very difficult the first time I did this at the new high school. I used to live in a rectangular room. Calculating the volume of the room wasn't a problem at all. My first year here, we started to do this, and I realized this is awful. I don't know if you have noticed that the front wall and the back wall in this room are not parallel to one another. That is the reason your desks are all wibble wobble and squiggled all sorts of different directions. Because if you set the desks up so that they're parallel to the front wall, it looks really stupid. If you set the desks up so they're parallel to the back wall, it also looks very stupid. I tried both of those things. And then I decided the only possible solution in a classroom this shape was to put the desks at all sorts of funny angles so that nobody noticed that your desks are not sitting relative to either the front wall or the back wall, because it looks silly regardless of which way you do it. So the first year I was here, we endeavored to measure all of the dimensions, figure out the angle of the front wall to the back wall, and also the little bend by the door. That's a 170 degree angle, I believe, right over there by the door. And then I thought to myself, this is silly. This is a brand new building. Somebody has the blueprints. So I sent an email to the district engineer and asked him if he could look at the blueprint to my room. Voila. Courtesy of the district engineer, the surface area of our room is 1,775.75 square feet. Beautiful. That is so much better than trying to calculate this based upon mathematical formulas, because this room is an absolutely absurd shape. So if we do that, and then use this little device, which I borrowed from Mr. Herding, which can measure the height from the floor to the ceiling. It's just a laser distance measurer. If I set this thing on the floor and hit go, .251 meters. So the height of our room is 3.251 meters. I think with all of that data, we should be set here to calculate the mass of the gas in our classroom. Now, you have lots of conversion factors available to you on your resource sheet, because already this is a real mess. Square feet, meters, we've got temperatures, pressures, we got all sorts of problems with the units. But remember, you've got help. Okay? You've got volume conversions here. A milliliter is a cubic centimeter. You have some length conversions, like meters to centimeters and centimeters to inches. You've got pressure conversions, you've got temperature conversions. Your green resource sheet is going to be a huge help. You may not use your Chromebook while you're doing this. I want you to actually muscle your way through using the things that are on your green sheet, because that's how you would muscle your way through in a test situation. And if you need some perspective along the way, I have set our cubic meter back up over here. So here's our cubic meter. This is a square foot. So I tucked that in the corner here so you can kind of see how a square foot looks relative to some of these other things. I put a 1 liter beaker in here so that when you calculate the volume of this room in liters, you can go, is that reasonable or not? And then I put the milliliter / cubic centimeter, and I put the 100 milliliter graduated cylinder. I basically put all that stuff there to help you along the way. So if you need some perspective, you can go kind of stand and stare vacantly into the cubic meter and see what you can do there. On the flip side of this is some space to do some calculations. And in the end, I want you to figure out the mass of the gas in both kilograms and pounds and make a comparison to what you decided. Okay, you can get to work.